Hi there. In our previous videos, we have referenced this idea that you could think of like a basis as like a set of axes that aren't necessarily perpendicular. And we want to be able to write a vector in terms of those axes, right? Figure out where they would lie along there. So in this video, we're going to talk about how to do that and then how to take a collection of vectors that are not perpendicular and make them so. Okay, and that's kind of where we'll be discussing in this and the next video. So to start us off, I've got a definition here. So definition 19, and you can pause to copy this down if you wish, says that given vectors v and w in Rn, so we're going to start out in Rn, the projection of w onto v is given by this formula here. So we're working exclusively right now in Rn, and we're using the dot product, so the inner product we're most comfortable with. So if I project w onto v, what that means I'm going to do is I'm going to take the dot product of those two vectors. Then I'm going to divide by basically the dot product of v with itself. That's the same as the norm of v squared. And then multiply that by the vector v. Now, if you're the sort of person who has difficulty kind of remembering formulas or getting kind of the order mixed up and what's going where, I remember this by whoever I'm projecting onto shows up all the time, and whatever's getting projected just shows up this one time in the numerator. So this formula, or the structure of this formula, is going to be key for us for moving forward for quite a bit. So let's do an example of this projection. So example 31 says the set UVW is a basis for R3 where U, V, and W are these vectors. We want to show first that this is an orthogonal set with the usual dot product. And then we want to find the projection of X onto each of those three vectors, where X is this vector here. So this first part showing that UVW is an orthogonal set with the usual dot product, that's a review from a couple videos ago. So pause the video here and see if you can do that. And when you're all done, the solution will be on the board and we will check our answers. Alrighty, so how did we do? So remember, in order to show that a set is an orthogonal set, you just have to show that the inner product of all of the vectors in the set is equal to 0. So in this case, we just have to show that the dot product between u and v, u and w, and v and w are all equal to 0, which they are. So this first part is very simple. We're done with that. This next part, gonna take us a little bit longer. Lenny is also displeased by that. So to find each of these projections, we're going to be using this formula. Now notice that this formula involves the norm of the vectors that we are projecting onto. So since we're projecting onto u, v, and w, I'm going to need to find the norm of each of those vectors. And then this formula also involves the inner product, or in this case, the dot product, between v and w. So in other words, because I'm projecting X onto U, V, and W, I'm going to need to find the dot product between this vector X and each of these three vectors here. So I'm going to think of this as like my mise en place. If I were baking, this is the stuff I'm going to get done ahead of time. And then I'm going to plug it all into the formulas and evaluate that afterwards. So I'm going to ask you to do the same thing. So what I'd like you to do is first pause this video. Well, first listen to the directions, then pause the video, I guess. So you're going to first find the norm of U, the norm of V, and the norm of W. And then you're going to find the dot product between U and X, V and X, and W and X. Okay, so those are 6 things that you're going to find. I'm going to do the same thing, but I'm going to pause the video while I work through it. And you're going to pause the video while you work through it. And then we'll both unpause, maybe even at the same time, who knows, and you can check your answers. All right, so get working on it and I'll see you in a moment. All right, so let's check our work. So when I found the norm of each of these three vectors, the norm is the square root of the vector dotted with itself. In other words, the sum of the squares of the coordinates. So 1 squared plus 1 squared plus a negative 2 squared gave me 1 plus 1 plus 4. And from that, I got the square root of 6. So that's the process I applied for the norm of V and the norm of W. So I got root 30 and root 5 for those. Then for u dot x, I did 6 times 1, which is 6, plus 0 times 1, which is 0, plus -2 times -15, which is 30. So it's my 6, 0, and 30. And from that got 36. And then I repeated that process for v and w, and got 0 and -15. So these are our components. We have our dot product and we have our norm. So now we just have to throw in the vector we're projecting onto and put our relationships in properly, and we can find these projections. So let's see. So let's do the projection of x onto u. And until I know this formula well enough to not have to like, oh, what was that formula again, right? Until I can just kind of recall it, I'm going to practice by writing it. So this is going to be u dot x over the norm of u squared times the vector u. So in this case, so notice the vector we're projecting onto, the u, that's the one that shows up everywhere. And then the x just happens this one time. So u dot x was 36. The norm of u is root 6. So we're going to have root 6 squared. And u is the vector 1, 1, -2. So root 6, if I square that, I'm going to get just 6. And 36 over 6 is 6. So I'm going to multiply each of these coordinates by 6. So that's going to give me 6, 6, and -12. So that's our first projection. Then we'll do a similar game for projecting onto v. So remember, our formula is going to be v dot x. And since we're projecting onto v, we're going to have the norm of v squared times v. Because we found these pieces earlier, it makes it easier for us. In fact, it makes it really easy because v dot x was 0. So we just have 0 times whatever. So this is going to be 0 times v, which is just going to be the 0 vector. What this means is that if we were thinking about what component of x does v contribute to, v doesn't contribute to this vector x at all. Okay, so it doesn't show up. So this is its projection. There's no piece there. And then lastly, let's do the projection of w, or sorry, projection of x onto w. So this is going to be w dot x over the norm of w squared times w. This time we don't get 0. So we have a -15 over the square root of 5 squared times w, which was 0 to 1. Now the square root of 5 squared is 5, and 5 goes into -15, -3 times. So we get 0, -6, -3. And there we go. Those are our 3 projections. Now, here's what this is telling us. So in a very simplified example here, let's say I have my usual set of axes, and I'm going to do an R2 just because it's easier for me to draw. When we think about what the projection is doing, let's say this is my vector. That's my point x. That's defining my vector. The projection onto the x-axis would be this component here. And the projection onto the y-axis would be this component here. So what we're doing is we're saying, instead of having these nice perpendicular axes, what if I have something like this? And now here is my vector x. Well, this is going to project onto here. So here's its projection onto that axis. And then it's going to project over here. So here's its projection onto that other axis. So that's essentially what we're doing. What we're doing is also an alternate way of finding the CBs. So I'm going to erase this a little bit. And I'm going to simplify these values to help us out here. So this simplified to be just 6, and this simplified to be a -3. And then this was 0, so that'll be 0. So basically what we have found is we have found the values for the coordinate vector of x in this basis. We know that x is going to be 6 copies of u plus no copies of v minus 3 copies of w. And if I were to add these up, I'm going to end up getting my vector x. So let's check. If I do 6 plus 0 plus 0, I get 6. 6 plus 0 minus 6 is 0. And -12 plus 0 minus 3 is -15. So that's how you can kind of check if you're doing all of the projections. They should add up to combine to be that vector x. And these numbers that we're finding, these coefficients, are the entries of the coordinate vector. They tell us how many of each of those basis elements we need to have. So there is a connection of this to what we've been doing, what we were doing a couple weeks ago when we were doing our linear transformations, and the coordinate vector was a transformation. So this is just an alternate way of thinking about that and working through that. So it turns out that these coefficients, right, we want to give them a name. We want to give this expression where we're writing in terms of these vectors a name as well. So we're going to define this as the Fourier expansion. So I'm going to write this definition on the board for us, and then we'll talk through it a little bit. All right, we came back. So here is definition 20. I'm going to get out of the way in case you want to pause it and write it down. But here's what it says. It says we're going to let V be a subspace of Rn with an orthogonal basis of V1 through Vk. So because V is a subspace, it doesn't have to have n vectors in its basis. It could be n or fewer. Then for every vector that is in this subspace, you can write that vector as a sum of that vector projected onto each of those basis elements. All this is doing is saying what we already know about a basis. We can write every vector as a linear combination of those vector elements. What this is telling us is a way to find the coefficients for each of those basis elements. This sum of using the projections is called the Fourier expansion, the Fourier expansion of x. And these values, okay, so these coefficients, are called the Fourier coefficients. So in the previous example, we had x was equal to, what did we get? We had 6, 6, -12 plus 0, 0, 0 plus 0, -6, -3. So this sum is the Fourier expansion of that vector x, which was, what was it? 6, 0, -15. So the Fourier expansion of 6, 0, -15 is this plus that. And the Fourier coefficients, the coefficient of u was 6, the coefficient of v was 0, and the coefficient of w was a -15. No, -3. Sorry. So, so those values would be our Fourier coefficients. So in this definition, in order to have a Fourier expansion, we are projecting, we're taking an element that's in our subspace and we're projecting it onto its basis. Now, maybe I'm something that's not in the subspace. So think about, for instance, if I'm in R3, well, let me back up a bit. Let's say I'm a point in R2. Sorry. I'm just going to back up completely. Let's say I'm a point hovering in R3. So I'm a point I don't know, I'm the point like right here. Now, if I want to project this point into R2, I'm going to see, okay, well, if I were to project it, it would land somewhere about there. So it would be, that would be its Y value, and that would be its X value. So this point here would be the closest point in R2 to this point floating out in R3. Because if it were to, the shortest, distance would be directly there. So that's going to be our next definition. So here, our Fourier expansion, we have a point in our subspace, then we can write it as the sum of the projections. For our next definition, we're going to take a point that's not in our subspace. So a point in R3, but it wasn't in R2, which is a subspace of R3. So a point that's in there, and we're going to see what's the point closest in there. And we're going to use the projections to help us out. So one more moment, I'm going to erase the board and write that definition for us to examine. All right, so I've cleared the board only to make it a mess again. Hooray! Okay, so definition 21 says we're going to let V be a subspace of Rn, and X, notice there's no line above it, so just X is a point in Rn. Then the orthogonal projection of X onto that subspace V is given by the projection of the point X onto the space V is going to be the sum of the projection of the vector X onto each of the VI's vectors, where those VI's form an orthogonal basis for V. In other words, I could have a point that's in my subspace, or I could have a point floating out and about that's not in my subspace. Kind of as we saw earlier when I was doing R3 with R2, right? So if I'm a point here in R3, to find the orthogonal projection into R2, I would kind of just drop that point into R2 and then find its projection onto each of those axes. And when I'm using these axes, I'm making sure they're perpendicular because we need to have an orthogonal basis. So we need to have orthogonal vectors in order to find this orthogonal projection. And the reason we want things to be nice and orthogonal is because of theorem 17, which says if you have this subspace and X is a point in Rn, then the orthogonal projection of X onto V is the point that's in your subspace V that is closest to that point X in your broader space. So if these are perpendicular, when we find that orthogonal projection, then that point that was out here, the closest point in our subspace to it is the point that's like dropped directly over there. So if you want to pause and copy this down, now would be a good time to do that, because we're going to work through an example of finding an orthogonal projection of a point. So I'm gonna erase the board now. So you might want to pause if you haven't yet to copy this down. All right, I hope you copied it down because it's gone now. So now we're going to do example 32, which says we're going to let V be the span of these two vectors that are in R3. And we're going to find the point in that space that's closest to this point here, which is in R3. So to do that, we need to find the projection of X onto the space V. Now, to help me with some notation here, I'm going to call this first vector V1 and the second one V2. In order to find this projection, I'm going to take the projection of the vector X onto the vector V1 and the projection of the vector X onto the vector V2 and add them up. And then if I had a third vector in here, I would add that third projection, and a fourth would be the fourth, and so on and so on. So remember me, this is our formula we want to remember. So we're going to have to find that. We're going to have to find two of these. So this is going to be V1 dot X over the norm of V1 squared times V1 plus v2 dot x over the norm of v2 squared times v2. Now, it depends on your personal preference, whether you like to keep all of your work within an equation, or if you like to break pieces out and set stuff up over on the side. So previously, when we did an example with projections, we found the dot products and the norms individually, and then we threw them all into the formula. So if you want to go ahead and do that for this problem, absolutely feel free to do so. Just so you can see a different experience, I'm going to do it all in this one equation so you can see if you prefer that method better. So I'm going to do v1 dot x. So that's going to give me 3, 0, and 0. Okay, so that's just going to be 3 over the norm of v1 squared. So this is going to be the square root of 1 plus 0 plus 1 squared times v1, which is 101, plus v2 dot x, which is, oh, this is easy. It's going to be 0 minus 2, 0. So again, we just get negative 2 over the norm of v2 squared. And so the norm of v2 is just going to be square root of 1 times v2, which is 0, 1, 0. Cool. All right, so 101 makes 2, and the square root of 2 squared is 2. So we get 3 halves, 101. That's just 1, so we'll get minus 2, 0, 1, 0. So we're going to get 3 halves minus 0, so 3 halves, or 1.5. 0 minus 2, so negative 2. And 3 halves minus 0, so 3 halves. So since we are trying to find the point in V that's closest to this point, we now want to take our vector notation and turn it into an ordered triple. So in this case, our answer is going to be the point 3 halves, negative 2, 3 halves. All right. And yeah, that's going to be it for this video. In our next video, so we've seen a little bit so far that orthogonality is a desirable property of collections of vectors to have. So in particular, if I'm out in this bigger space and I want to find the point that I'm closest to in a subspace, then having this orthogonal basis is going to be necessary and important. So what we're going to do is we're going to take this concept of a projection. We've been living in Rn, but there's no need for us. We can take this concept and generalize it to any inner product. Well, that was a terrible place for me to write that. But what we're going to be doing is we're going to be generalizing this to any inner product. And we're going to be seeing how can we use this to help us create an orthogonal basis for a set. So if I have a set of axes, but they're not perpendicular, how can I use them to find one that is? So that's where we're heading in the next video. This concept of projection I find really neat. If you haven't read it before, but you're kind of interested in geometry and math history and this kind of things, I'd really strongly recommend you read the book Flatland by Abbott. It's a satire of Edwardian society. So be prepared for women and marginalized groups to be treated like crap because he was, he was satirizing society basically. So he was like pointing out the flaws in the society. So yeah, it's a it's a tough book to read if you don't read it through that lens. But what's really interesting about it to me is, so the concept of it is like square is a shape that's living on a whiteboard. So he's living in 2 dimensions. And he has this dream of visiting a single line. So here's the line, and here is square. Well, pretend that's a square. He's living outside the line. And then there are line segments who live on the line, right? They're like this. And so square decides to visit line land. That's what that's called. So square visits line land. And when he does, he's overlapping it. but all the lines can see or acknowledge is this piece of square that's in it. All they can see is the projection of square onto that line. And so square is trying to tell them, well, there's not only forwards and backwards, there's also like left and right. And the lines have no concept of what that means because there's no left or right. They only exist in this world of the line. And then Square also has another dream where he visits the world, or he has a visitor from our world, from R3, and Sphere comes to visit him. But when Sphere comes to visit the whiteboard here, three-dimensional Sphere can't fit on the whiteboard. So its projection just ends up being a circle. And as Sphere passes through, right, think about a ball passing through the whiteboard. The smallest piece would be like a point as it goes through. And then as you go towards the middle of the ball, it's going to get bigger and bigger and bigger. And then it gets smaller and smaller and smaller again. So this is what Square witnesses. He witnesses Sphere changing size as he passes through Flatland. And so they have this kind of conversation about, okay, well, what would R4 look like? What would a fourth dimension look like, or a fifth dimension? And I just think that that concept is interesting, thinking about, aspects of our universe that are bigger than our brains can conceive or understand. We can only understand fourth dimensional objects as a projection into a three-dimensional world, because that's the world that we live in and that we understand. So what components of the fourth dimension are we missing because of our necessity to understand in terms of projections? So yeah, anyway, Project Gutenberg has it. The copyright has expired basically, so on Flatland. So there was also a movie made about it, which I haven't seen, but you could check it out. You might find it on YouTube even for free. So yeah, Flatland, Edwin Abbott. Give it a read if this kind of thing is interesting to you. But again, it was written in I think the 1800s, so little archaic language and societal values. So that's it for this piece. I hope you enjoyed the video. And yeah, I will see you in the next one, where we talk about the Graham-Schmidt process, which is going to be generalizing all of this stuff to bigger spaces. So see you then.